Welcome back, guys. Today we're going to examine two traits simultaneously in a genetic cross. We call those dihybrid cross, or dihybrid crosses. Again, what we have here is a dihybrid cross, and we're going to work a couple of problems like this and give it a look, and it'll be a problem set that's posted with 6 of the original monohybrid cross with just one trait, and then 6 with these two trait problems. So if dihybrid crosses win, we are going to examine you're examining two traits in the problem simultaneously. And we are going to assume independent assortment. What we mean by that is that these traits, they're going to be located on different chromosome numbers. Right? You might have eye color on chromosome number 5 and then hair color on chromosome number 6. So both traits won't be on chromosome number 5. We're assuming that they're on different chromosomes because that allows us to establish a pattern of ratios that we can use to solve these problems. All right, so yeah, we're going to sketch out what we're talking about here. Here's a cell, here's the nucleus. And similar to how we've operated in the past, we're going to show these chromosomes. So I'm going to show here's chromosome 1 from dad, chromosome 2 from dad, here's chromosome 1 from mom, and chromosome 2 that is individually received from mom. And we're going to then sketch out these chromosomes off to the side. So let's show this chromosome that came from dad. So right here. And chromosome 2 from dad, we're going to show over here. 2 from dad. All right, we'll do the same thing with mom. So with moms, we're going to have chromosome 2. And this is chromosome number, we're going to say number 1. It should probably become a little bit more. That makes sense. Chromosome number 1 from mom. And then chromosome number 2 from mom. And so we're saying we're looking at two different traits. So let's say that we're talking about fruit flies. And fruit flies, we're going to say they can have red eyes, which is dominant over white eyes. We'll say red eyes. Or they can have these white eyes. And red is dominant over white. And we'll say that they can have normal wings. Or they can have these small vestigial wings, or we're just going to go with wingless. So they can have normal wings, or they can actually be flies that don't have wings. They kind of look like ants. We're going to say those are wings. So let's say that we're looking at an individual here that is a heterozygote. Heterozygote, which means they have both versions of each trait. So what that looks like would be on the chromosome for eye color, we're getting red eyes and we're getting white eye allele, heterozygous for eye color. On the chromosome for wings, we'll say they have a wingless and wing. So they got both. They got both versions of the eye allele, both versions of the wing allele, which means their genotype is going to be big E, little e, big N, little n, because the genotype is just the characters or the symbols that represent the gene. And then the phenotype, what it looks like, the description, will be a red eye, so because it's got a red eye allele that's going to dominate over the white eye allele, and it's going to be normal wing. And that's going to dominate over the wingless allele. We got red eyes and normal wing. So what we want to do is we're going to do a Punnett square. And we're going to cross two flies, both heterozygous for these traits. So let's say that you were asked to breed two flies that are both heterozygous for both traits. And they want you to find the phenotypic ratio. Find the phenotypic ratio. So we're going to breed two flies, both heterozygous and both traits, eye color, wing variety. We want to find the phenotypic ratio. So first thing that we do, we go ahead and identify what our parents are. So let's say that parent one, the male, is big E, little e, big A, little n. And we're going to breed that with the female. That's also big E, little e, big N, little n. Now, where did this come from? These genotypes, they came from up here, both heterozygous, both flies heterozygous. So let's go ahead and break this apart. And there's two ways to do this. One way would be to draw a big 16-box Punnett square and work through that 16-box Punnett square, showing all of the different options that are possible with independent assortment. Or we can separate them as two independent events and use what's called the fractional method. So for me, that is the way that is easiest and makes the most sense. So in our F1, we're going to take the eye color, and we're going to look at that over here, independent of the windshield. So we're going to take these E's. So we're going to take the genotype for eye color from one parent. We're going to take the genotype for eye color from the other parent. And we're going to set them on this Punnett square and on the Punnett square. We can see kind of our result here. Again, we're looking for a phenotypic ratio, so we don't necessarily need to list out all the genotypes and the fractions. So we're going to see that 1, 2, and 3, because the red eye allele dominates over the white eye allele. 1, 2, and 3 have red eyes here. So 3 out of 4 have red eyes. Meaning 3 out of 4 have at least one dominant version of the allele. It doesn't matter with the other ones. It could be a big E or it could be a little e. It's going to fall into the same big, the same fraction. That leaves us with just 1 out of 4 having white eyes. And that'll be the little e. We're going to do the same thing with the wings. And we can already see, because the wing genotypes are the same, they're going to play out the exact same way the eyes genotypes did. But in case you would have a problem where they weren't the same, this is how you would do it. You would set this up, bring the wings over here, independent of the eyes, because again, they're not linked genes, they're independent. We're going to get the same type of Punnett square that's created. And we're going to say that 3 out of 4, again, wings, 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 have wings. So we can dominant allele. And then 1 out of 4 are wingless. And they don't have wings. Now, how do we go about figuring out what the ratio of the offspring is for the phenotypic ratio? What we have set up here is a nice system that we can use just to start multiplying these fractions. So, how many have red eyes and wings? We're just going to multiply the red eye fraction 3/4 times the wing fraction 3/4. So it's 3 1/4 times 3 1/4 gives us 9/16. So 9/16 have red eyes and wings, or white eyes and wings. We're going to do 1/4 white eyes times 3/4 for wings. That's going to give us 3 out of 16. So 3/16 is the chances we have like often with red eyes. And these are odds. How about red eyes and wingless? We're going to go red eyes at 3 1/4 and 3/4. We're going to go wingless at 1/4. That's 3/16. And finally, we have white eyes and wings. That's 1/4 times 1/4, 1/16. So our ratio is just taking the top part of that fraction and comparing them. So we have a 9 with 9/16 to 3, 3/16 to 3, the other 3/16 to 1, 1/16 ratio, phenotypic ratio. And that would be our phenotypic ratio. We have a 9 to 3 to 3 to 1 phenotypic ratio in terms of the offspring. So how do we use this? So let's show you how you would use this ratio. So let's say that we had a problem where they said, so how many flies? Let's say we have how many flies in a brood, which is a group of 1,500 flies, will be red eyes, or we'll say will, probably better way to say it, have red eyes and no wings if, we'll say both parents are heterozygous for both traits. So how many flies in a brood of 1,500 flies will have red eyes and no wings if both parents are heterozygous for both traits? Now we've done all the work for that already. Right? We did all the work right here. And what we want to do then is find our fraction for red eyes and no wings. Red eyes, no wings, 3/16. So we're going to take that 3/16 fraction, and we're going to multiply that by our brood size, which is 1,500 flies. And that'll give us approximately 281 flies. So that's how you can estimate the number of flies with your phenotypic ratio that you have figured out from the problem. Okay, so that's Dihybrid Crosses. You can see 6 problems like that on the problem set. I hope that's helpful. If you have questions, next Friday we'll do the Q&A and you can ask them then. See you next time.